All right, so the B4 notes look at exponents and exponential functions. This first section is just a review of simplifying expressions that involve radicals. The cube root of 64 means what number do you multiply by itself 3 times to get back 64? And so the answer here is 4. The cube root of 125 similarly would be 5, since 5 times 5 times 5, or 5 to the third, gives you 125. The fifth root of 32 is 2, because 2 multiplied by itself 5 times gives you back 32. The square root of 100 is 10. Remember, when there's no index on the radical out here, there's an invisible 2 that we don't write. The square root of 225 is 15. And then lastly, the cube root of 729 would be 9, because 9 to the third would give you back 729. Another way that you can see radicals represented is by rational exponents. And so here in example A, where it says to find the value of each expression, 121 to the 1/2 is the same thing as the square root of 121. So you want to think about it like the number on the bottom would become the index of the radical if you were going to write this in radical form. The square root of 121 is 11. So we don't need to rewrite it in radical form if we can do that in our heads. The fourth root of 81 would be 3, because 3 times 3 times 3 times 3 would give you back 81. The fifth root of 32 would be 2. We already did that one up above. Down here in D through F, these problems have an additional step, so I will rewrite these. The denominator of the rational exponent becomes the index of the radical. So 125 to the 2/3 power becomes the cube root of 125 squared. We can do inside the parentheses first here. So the cube root of 125 gives me 5. And then when I square 5, I get 25. So my answer to this one would be 25. I'll do E and F similarly. The number that's in the denominator of the rational exponent becomes the index of the radical. So here it's the fourth root of 81 raised up to the third. The fourth root of 81 is 3. And then 3 to the third gives me 27. And lastly, the fourth root of 625 raised up to the third power. So the fourth root of 625 is 5, because 5 times 5 times 5 times 5 times itself 4 times gives you back 625. And then when I do 5 to the third on this one, I get 125. So if the numerator of the rational exponent is the number 1, you don't have that second step that you need to do. But if the numerator on the rational exponent is the number besides 1, then sometimes you have a second step that you'll need to do to simplify each expression. The next example wants me to determine whether the following equations are true or false. So I'm going to simplify the left-hand side, simplify the right-hand side, and then I'll compare them to see if they're the same or if they're different. The square root of 1024 is 32. And then on the right-hand side, it becomes the square root of 4 raised up to the 5th power. The square root of 4 is 2, and then 2 to the 5th power gives me 32. So since these two numbers are equal, we would conclude that this one was true. On B, I'll put the denominator of the rational exponent becomes the index on the radical, so the cube root of 8 squared. On the right-hand side, the square root of 64 becomes 8. So the cube root of 8 gives me 2, and then 2 squared gives me 4. These are not equal to each other, so we'll conclude that this one is false. The cube root of 64 is 4, and the square root of 16 is 4. And so here, since these two are equal, we'll conclude that that's true. On D, 2 to the third gives me 8. Over here, I'll put the 3 underneath the 6 in the rational exponent. 6 divided by 3 gives me 2, and 8 squared gives me 64. So since these two numbers are not equal, we'll conclude that D is false. On this next example, we're practicing writing a radical expression in exponential form. So the number that's out front, the index of the radical, becomes the denominator of the rational exponent. This first one would be b to the 4 over 3. Be careful, if you write the fraction upside down, it's not correct. On the next one, it's an invisible 2 that's out front. You can write it in if that helps you. So this one would be d to the 3/2. And then lastly on C, be careful because the 3 and the x are together inside parentheses. And so the 3/4 exponent goes outside those parentheses and would apply to both of those values on the inside. All right, here in this next example, a student rewrites the expression in radical form as follows. What mistake did the student make, and what is the correct form of the answer? Notice with the way the directions to this question are written, it is assumed that the student did make a mistake. We're not trying to figure out if they made a mistake, we're trying to figure out what the mistake they made was. So when I'm simplifying this expression, remember the number that's in the denominator of the rational exponent becomes the index on the radical. So comparing this to the student's work, it looks like the student has the numbers backwards. So the mistake that was made is that the denominator should go out front and become the index of the radical. In the student's example, they put the numbers backwards. And so to correct this, the 3 should become the index on the radical, and then the squared should stay as the exponent on the expression. Make a note that it's correct for the squared to be underneath the radical or inside the radical, or it could be written on the outside as well, like we've been writing it so far in the notes today. All right, on this next example, we're asked to rewrite the radical expression. And so there's no number given out front as the index, so we know that that means that it's a 2. Remember that the 2 will come over here underneath, and so the 1/2 exponent will become the exponent on the expression. So the first thing I'll do is I'll rewrite it like this. So it's going to be 10x to the third, y to the eighth, z to the fifth, and then the exponent here is 1/2. So that's the first step in rewriting it with radical exponents. Once I've done that, the next thing I'm going to do is I'm going to shower the power. So that 1/2 exponent will get showered to the 10, to the x to the third, to the y to the eighth, and to the z to the fifth. And so you're going to raise each of those up to the 1/2 exponent, or if they already have an exponent, you're going to multiply those exponents together. So 10 to the 1/2, x to the 3/2, y to the 8/2, and then z to the 5/2. And there's one more thing I can simplify on this one. So 8/2 on the y would divide to give me 4. And so that'll give me my final answer for this one. All right, here we're being asked to identify the correct number to rewrite the expression as a single term. So the question mark right here on the x, that's the number that we're trying to figure out. Notice that there's x's in the top, there's x's in the bottom of this fraction, there's numbers that are underneath the radical, and then there are some numbers that have rational exponents. So I'm going to start by rewriting the left-hand side of the equation all as having rational exponents. So this will be 1/4, this will be 1/3. Also notice that the x to the negative 1/2 is raised up to a negative exponent, and so I'll move that to the bottom of the fraction to clear the negative on the exponent. So this is what I'll have once I make those simplifications. Now, in order to combine these like bases together, I need to make my rational exponents have common denominators. And so here the common denominator would be 12, and so I would get 3/12, 8/12, 4/12, and 6/12 when I make them have a common denominator. The next thing I'm going to do is I'm going to multiply together the like bases in the top, and so when I do that, the rule says that I add the exponents. So in the top, I'll get 11/12, and then in the bottom, I'll get 10/12 as my exponents. The last step I need to do is I need to apply the division property of exponents, which says that when you're trying to simplify and the bases are the same, you subtract the exponents. And so here, 11/12 take away 10/12 will give me 1/12 in my exponent. The question asks us to identify the correct number to rewrite the expression as a single term. And so the answer for this question is the number 1/12. 1/12 is the number that you would need up in the exponent right here to make this equation be true. All right, the last example on this page is a little bit tricky. Are the absolute value symbols needed in simplifying the expression below? Explain your reasoning. So the sixth root of -8 raised up to the sixth power equals the absolute value of -8. You're being asked to come up with an argument about whether these absolute value bars on the -8 are necessary. -8 raised up to the sixth power would give you a positive number, and then the sixth root of that positive number would yield +8. You might think about simplifying this by moving the 6 and putting it in as the denominator of this rational exponent here. If you did that, -8 would be raised up to the 6/6 power. 6/6 would give you 1, and you would get -8 to the first power, which would give you -8, but that's incorrect. You won't get -8 when you simplify this radical expression. The value would need to be +8, and so here we can conclude, yes, the absolute value bars are required here for these expressions to be equivalent. The sixth root of -8 raised up to the sixth power has a positive value, and so in order for that original expression to be correct, you would need the absolute value bars around the -8 to make those two expressions be equivalent to one another. All right, an exponential function is a mathematical function of the following form. Exponential functions represent situations where numbers are increasing by a factor. In this first example, it says that zombies spread at an exponential rate. It says there will be 5 times as many zombies as there are in the previous day, starting with just one zombie. So the first thing we're asked to do is create an exponential model. Y equals the a value that goes out front is how many you start with. So in this problem, there is one zombie to start with. And then it says that each day you're multiplying times 5. So you start with 1, and then each day you're multiplying times 5. In the next part of the question, it asks us to figure out how many zombies would there be after 12 days. So I'll plug in a 12, and I'll use a calculator to evaluate that. So after 12 days, there would be 244 million zombies if they grew times 5 each day. So exponential functions often grow very quickly. In the next example, you're given the graph of an exponential function. The first question asks, what was the concentration of the medicine when it was first injected? Your y-intercept shows you the initial value. So here we can say that the initial concentration of the medication was 100 milligrams per liter. The second question asks us a true or false question. It says the concentration of the medicine decreases more in hour 1 than it does in hour 5. So in hour 1, the concentration of the medicine decreased here, what I've highlighted in yellow. In hour 5, the concentration of the medication decreased this much that I've highlighted in green. And so we can conclude here that the answer to the question is true. The concentration of the medicine decreased more in hour 1 than it did in hour 5 because in hour 1, it was going down more quickly. Question C says, how long did it take for the concentration of the medicine to reduce to half? So for this one, if it starts at 100, we want to figure out when does it get down to 50. So looking at the graph, it gets down to 50. This is when it equals 50. And And then I'll go down to my x-axis and I'll answer this question that it takes 2 hours for it to reach about half of its initial concentration. And then the final question in this section says, what happens to the concentration of medicine after 8 hours? So here is hour 8 over here on the right side of the graph. At 8 hours, the concentration of medicine would continue to decrease slowly. There's nothing to indicate that it stops at 8 hours. However, it would eventually run out. If we know 2 points that are on the graph of an exponential function, we can use those points to figure out the exponential model that represents the data. So knowing that these are exponential functions, I can use the points that I'm given to figure out the multiplier and then to work backwards to figure out the starting value. And I can use those two things to write the answer to the question as an exponential function. So on A, to turn a -4 into a -16, I'm multiplying times +4. That's one of the numbers that I need to know. The next thing I need to do is I need to expand the table a little bit. Right now, all I know is that 2 goes with -4 and 3 goes with -16. But in order to write the exponential model, I need to figure out the number that goes with 0. In order to figure out the number that goes with 0, I have to work backwards first to figure out the number that goes with 1. If I'm multiplying by +4 to get to each number in the list, I'm going to work backwards and I'm going to divide by +4. So the number that goes with 1 would be -1, and then the number that goes with 0 would be -1/4. When I write the exponential model for the data, I'm going to start with y equals. The number that pairs with 0 goes out front. That's my initial value. And then the number that goes inside the parentheses is the number that I'm multiplying by each time to get to each next number in the list. So here for this first problem, it would be y equals -1/4, and then 4 goes inside the parentheses because you're multiplying by 4 each time to get to each next number in the list. I'll use the same process on B. So B is a little bit different because they tell me that 1 goes with 1 and 3 goes with 1/25. So I'll need to figure out the number that goes with 2 to figure out my multiply pattern, and then I'll have to work backwards to figure the number that goes with 0 to figure out my initial value. So the numbers are getting smaller. I have to know what do I turn a 1 into that I can then multiply it by the same number to get 1/25. So the pattern has to work for everything. Analyzing the numbers on this one, if I times 1 by +1/5, I would get 1/5 here. And then if I times that by 1/5 again, I would get 1/25. So the number that you're multiplying by on this one is 1/5. And then you want to work backwards to figure out the number that goes with 0. So instead of timesing it by 1/5, I would times it by 5, or I would divide it by 1/5. And so that would help me figure out that the number that goes with 0 is the number 5. To write the exponential model for this one, I'll do y equals, the 5 goes out front, and then the 1/5 goes inside the parentheses. It's a coincidence that on these two problems, it's the number and its reciprocal in the question. Oftentimes you'll have completely different numbers as both the initial value and as the multiplier. All right, in the next question, compound interest is interest on a loan that's calculated based off of the initial principal and then also accumulated interest from other periods. And so this formula right here is the compound interest formula. And so we'll be using that to answer some questions today. In the formula, you see that P is the principal, that's the initial amount that gets invested. R is the interest rate, which is calculated as a decimal. N stands for the number of times per year that the interest is compounded, and this is something that people sometimes struggle with. So if n equals 1, that means that it happens once each year. If n equals 2, that means that it happens twice each year. But oftentimes in the word problems, you'll see the words quarterly, monthly, daily. So it's important to think about it as how many times per year is it happening. And then lastly, T stands for the time in years of the investment. So a problem to practice with, if you invest $100, that's your principal, at the given rate compounded quarterly. So here quarterly means my n will equal 4. How much money will you have after 10 years? Your first job is to put all of the numbers into the formula correctly. And so here I've done that. The 100 goes in first because that's your principal. The interest rate, the decimal place, moves 2 places to the left, and then that turns into 0.0377 for your interest rate. The 4 goes in the denominator because that's your n, that's your quarterly compounding. It happens 4 times per year. And then up in the exponent, you put the 4 for the n, and then times t, it says 10 years in the question. Once you have all of the numbers in the right spot, then you just need to use a calculator to type this in. You might simplify it a little bit first. On this one, when I type it all into a calculator and I round my answer to 2 decimal places because it's a monetary answer, I get $145.53. That would be the new value of the investment after the given amount of time at the given rate. The last example on this page gives us a formula where the numbers have already been filled in and asks us to figure out how many times per year is the interest being compounded and how do you know. So remember, n is the denominator underneath the rate. It's also the number that comes in front over here in the exponent. In this question, n equals 12, and that means that the interest is being compounded monthly. Make a note on this one that says The more often interest is being compounded, the more money the initial investment will make over the same amount of time in the same account. Obviously, if the investment is being made over a longer period of time, that will also yield a bigger return. If you were looking at the same investment at the same rate for the same amount of time, the one that's compounded more often will yield a bigger return, so you'll get more money. All right, and here on the last page of the notes, we're going to solve exponential functions using logarithm. Notice that on both of these equations, the x is up in the exponent. That means we're going to need to use logs to get the x out of the exponent. I'll start with example A. So here I'll begin by adding the 4 to both sides. I'll get 5 to the x exponent equals 11, and to get the x out of the exponent, I'm going to take the log of both sides. So I'll get log of 5 to the x equals log of 11. The x that's up in the exponent can now come out front, and then the final step I need to take to isolate the x is I'll divide both sides by log 5. The question wants me to write my answer as both an exact solution and rounded to 3 decimal places. And so here my exact solution would be log 11 divided by log 5, and then typing that into a calculator and rounding it to 3 decimal places, I'm going to get 1.490. So these would be the two ways of writing the solution to this first equation. The second equation has a few more steps. I'm going to start by adding the 10 to both sides. Once I have the base isolated, I'll take the log of both sides. I'll apply the property of logs that says that the exponent comes out front. Next, I'll divide both sides by log 6. Remember, I'm trying to get the x all by itself. So now I'll add the 9 to both sides. And then lastly, I'm going to divide both sides by 3. So written as an exact answer would give me this. And then when I type that into a calculator and round it to 3 decimal places, I get that my answer is approximately 3.362.